Hello and welcome to the Alternative of Code 2021, day 11, part 1. Today we are given a problem that, to be honest, is quite complex in the description, so I think we'll have to go through a few steps to examine the output and see what's happening. Essentially, we are giving a grid, a matrix of 10 by 10 elements, so it's always 10 by 10, and those elements represent octopus that at every step will increase by 1. So this octopus is 5, next step will be 6, and so on. But when an octopus reaches 9, it flashes. And you can see the flashes highlighted here. The flashes also have the effect that they increase of 1 all the neighboring octopuses, including the ones on the diagonal. So for example, this 9 will increase this one, not just by, will increase this one, this value in the corner, because you can see that in the next step, instead of becoming 2, which would be just the normal increase that is required by the problem, becomes a 3. Same goes for this one, which increases by 2 because it's close to this octopus and this other, so it receives 2 flashes. And this central one is a particular case because it doesn't just increase by 1, so it doesn't simply become 2 on the next step, but it increases by 1 for each neighboring octopus that also flashes. So this is increased so much that it flashes. It's quite a strange problem. What we're asked to do is to calculate the flashes of octopuses over time and how many flashes are there in a given amount of steps. So for example, after 10 steps, here there are 204 flashes. Another important thing to notice is that when an octopus flashes, it reaches the value of 0 no matter what on the next iteration. Notice that if an octopus flashed and also received flashes from others, its value would be greater than 9 in theory, but the problem states that they have to reach in any case the value 0. So it doesn't matter how much energy it had, how many flashes it received, it's always 0. Since the problem is quite a bit strange, I prefer to work first on the solution, on the small problem given by the description itself, check that my result is the same as the problem description, and then when I'm sure, I go with the real input of my problem, so I can check and compare, since the problem description is quite a bit strange. As usual, I have my scaffolding. I already have day 11, in this case not my input, but the example input that is in the problem. Let's start by parsing it. So I create a grid, which is an empty grid, and then for every line in the input, I add to the grid, so append what happened here. I add to the grid the values that are in this line. So the integer v for v in line dot strip. Dot strip again because we have the new lines and empty lines, so we just want to ignore it. And after that we pass it to part 1, which we have to implement. So part 1 will receive a grid. What do we have to do? As we saw before, when we have a problem that is based on some state that evolves in steps, a good idea is to represent this step with a function. So we'll have at any step, so for s in how many steps are we required to simulate, it's 100, I think. I saw it earlier. 100, yes. But let's start with the example solution, so the first 10. Then we will just change this into 100. So for each step in this value, we will create a function that will calculate for us the next state of the problem. So the grid will be equal to next step of the grid itself. So this next step function is the place where we will put the logic of our problem. Since at every step we also have flashes, we require this function to give us the list a number of flashes that we had. So flash count, let's call it. And now what we want to do is simply to print the grid, so I can see how the grid evolves. This is not quite a problem, but it makes it a lot easier to debug. And I also want to keep track of the flash count. So I create a variable that I call total flashes, initially 0, and then I simply increase the total flashes by the number of flashes that we had in this example, and I print, just to be sure, the step, which is S, and the total flashes. Let's also print the flashes in this instance, so that it's easy to track what's happening as we debug the problem, because I don't think it will be correct in the first instance. Total flashes. Okay. Now we have to implement this next step function. So we define the next step. This next step function will receive a grid, which is a list of lists of integers. The typing is not necessary, but it makes it a bit easier to understand what's going on. And we return us a tuple, because it returns two values. The first one is the same as the input, because this is a step function, so it has to give us back the same thing that we gave it as an input, with the same shape, at least, same shape and type. And then it will also give us the flash count, which is just an integer. Okay, and this is basically the logic that we want to implement. Now we have to actually implement the evolution of the system. Let's see, the problem already is nice enough to give us 3 steps. So first, the energy level of each octopus increases by 1. Now, one thing that you have to consider when you implement a sort of evolution problem in which a state evolves is that you want usually to create a new state that we call new grid, and only read from the old state and write to the new one. This is because, since the problem may have different rules according to which the system evolves, if you write to the grid, which is the input, and then read it, you will end up essentially reading what you just wrote, not the original state of the system, and it's a mess. It can be done sometimes if you know the rules of the problem. You can easily keep track of what you wrote and what was already there. But to be sure, I create a new grid, which will be essentially an empty grid. Now, what do we do here? We say that the new grid will go for, will contain a row that we are going to define later for every, it doesn't matter what, for everything that is in the range of the grid. What is the range? Is just the side of the grid. The problem states that this side is always 10. So I simply create a variable here, a constant, and I call it 10. Side, and it's 10. Yeah. What is this value? This is a row, so it's essentially number 0 for some values we don't care about in the range side. So this is simply creating a new completely empty grid with the same sides of the, I say side, it's sides actually, sorry, I mean it's the side of a square, that's why I call it side, but side is a bit more intuitive. Now we create an empty grid and we increase the level of energy for each octopus by 1. So we go through the element in the grid, so we'll say for x in range, sides, and for, oh, what happened? Okay, for x in range sides, and for y in range sides. This is ugly, so I create an helper for that I call it all coordinates. So def all coordinates. this is simply a short way to do this, because I do not want to put a lot of force inside force that is ugly. I just yield x and y. So now I simply created this generator that goes through all the coordinates and give me them immediately. So I just say for x, y in all chords, easy peasy. What I do, first step, I want to calculate the energy level for each octopus, which is the previous value plus 1. So new grid in position x and y will be equal to the initial grid in position x and y plus 1. So far, so good. This is the first step. Then it says that for any octopus with an energy level greater than 9, we have a flash. And when this happens, all the neighboring octopuses have an increased energy level, increased by 1, including diagonals. And then, if they reach a level that is greater than 9, they also flash. So a flash can trigger other flashes in a sort of cascade. And this continues as long as there is no new flash. But one essential thing to notice is that a flash can happen only once per step. So we have to calculate the flashes. If those flashes trigger other flashes, we calculate them, which means we increase also the energy level of the octopuses that are close to the new ones that flashed, which in turn can trigger other flashes, which requires us to calculate again what is the state of the other octopuses, with the rule that we do not trigger a flash more than once. This is essential because if you think about this problem, when a flash can trigger a flash that can trigger a flash, you may end up in a situation in which essentially a chain of flash is infinite. But we have a condition to stop, which is that every octopus can flash only once. So let's implement let's put a comment here. Step 1. How do we call it? There is no name for this part, so let's call it step 1. Increase of 1 energy levels. And this is the simple part. Then step 2. Calculate the flashes. An octopus flashes at most once. Every octopus can flash only once, so this is essential for our problem. And now what we do is we iterate over the octopuses, we calculate who flashed, and when we do, we keep track of the list of octopuses that did a flash and increase the neighbors. And we repeat this operation until there are no new flashes. This is essentially very similar to a graph exploration, so we need some set to keep track of what flashed or not. So first we create a set of the octopuses that flashed. So flashed is equal to a set initially empty. This is going to be the list of all the octopuses that had a flash. A set. Then what we do? We iterate over the others and we go forward until we see that there are no new octopuses to flash. So I implement a while true. There are many ways to do that, but I prefer to say, okay, I want to go forward an infinite amount of times until there are not new flashes at all. So in this while cycle, I will have a set of the new flashes, which is equivalent, if you watch the videos of the previous problem, to the edge of the exploration of this state. So essentially, we put in here everything that is changed. So new flashes is equal to a set, initially empty, of course. And then we want to go through all the coordinates that are in here. So luckily I can use this helper again. And for each one, I check whether the new grid at position x and y is what? Greater than 9. So there is a flash. if there is flash, then the first thing we have to do is to check whether this flash is already in the ones that we know. If it is, we do not want to explore it, because it's something that we already explored. We want to detect only what is new. So I say that if xy is in flashed, actually is not in flashed, then fine, we found an octopus that did flash in this instance. So first of all, we keep track of it. So we say the new flashes dot add xy. So we keep track of it. This is what we will later use to decide whether there were news where we found something or not. So we need to keep track of what did flash. And now that we found it, we have to actually trigger the flash, so increase the neighbors of 1. So what we do is we have to go through all the neighbors, which we'll do in some helper to make the problem a bit more readable. And x and y will be the coordinates of the neighbors in neighbors of x and y. We just increase then the grid for x and y. We are going to define this function later, of course. So at the moment I'm focusing on the logic of this flash thing, not on how to find the neighbors. This function will give us all the coordinates that are around a given one. And now what we do? We went through all the coordinates, we trigger all the flashes. What we want to do is to check whether there were new flashes, something that we found. Notice that since we checked that a flash was not in flashed, everything that we have here that is in new flashes is completely new, something that we explored. So we say that if the length of new flashes is equal to 0, this means that we didn't find any new octopus to flash. All of them were explored, so we can break the cycle. Otherwise, what we do is we put the new flashes in the list of flashed octopuses, because we already know that they flashed, so we just keep track of them. So flashed is equal to flashed dot union of new flashes. This union can be transformed also in something like this. This is a bitwise OR, and is equivalent to doing the union. Or I think it's also possible to do this. At least it's possible in Java. Yeah, it's not complaining, at least my editor. So this simply means, okay, flashes is equal to the previous flashes plus the new ones. And that's it. So now we calculated the new flashes until we found something. We still have to implement neighbors as a function that will give us the coordinates around a specific cell. And what we have to do, the problem says that after we calculated all the flashes, we have to reset the energy level for flashes that are for every octopus that flashed. So if they reached 9 or above it, we reset it. So step 3, reset to 0 the flashed octopuses. I wonder what one will think seeing the comments of this problem without knowing the context. It's a very weird description, but that's the fun of it. This is simple because we have the flashed, which is a set of all the coordinates that we just flashed. So we just say, okay, for x, y in flashed, we reset it. So we say that the new grid at x and y, it doesn't matter what it was, could be could be 9, 10, whatever. We just reset to 0. And this is the solution. So the step function, we want to calculate the next step as a return value. Now we did everything. The new grid is complete in theory. We just have to return it. So I return the new grid, and the amount of flashes, which is just the length of, what is it, the flashed set. That's it. What we miss now is the neighbors function. So def neighbors. This function here, what does it do? Given a coordinate xy of a cell, tells us all the valid neighbors. So we explore the diagonal, so we say that for dx, where d is, let's call it ox, so the offset of x that is between -1, 0 and +1, and also for the same in y. So essentially we explore all the variation that are, or the possible offsets that keep track of the adjacent cells. We have all the possible coordinates that are around the cell x and y, but some of them are not valid. First of all, we have one case, which is when ox and oy are both 0. So if they are, so if ox and oy, or let's say ox equals 0 and oy equals 0, we ignore it because we are moving off 0 in both cases, so we are giving back the original cell. So that's not something that we want. That's fine, so we ignore it. Another thing we want to ignore is the case in which we are on the edge of the problem, on the edge of the grid, and the problem doesn't say that we have to wrap around the border. So essentially, we ignore neighbors that end up being outside the cell. So how do we calculate it? We simply state that if x plus ox is greater than the size itself, or x plus ox, so the eventual coordinate, is lower than 0, we continue, we skip it because it's on the edge, which can be on the right or the left side. Same thing goes on with y, so I just copy the code. So y, sorry, I hate winter. And that's it. So we skip it, the cases that we want to ignore. So the cell itself, all the cells that are outside the edge of the grid. And now we just yield x plus ox and y plus oy. So this function will give us all the neighbors. Let's create a small docstring. Generator of valid neighbors, including diagonals. And that's it. Neighbors is here, it's done. We get the flash. Okay, so in theory this should be enough. So let's run it and see what happens. Advent 21, this is day 11. Okay, and there is an error. The error is that the list index is out of range in this part. So neighbors is not actually retrieving all the... it's actually not filtering correctly the range, because here I didn't put an greater or equal. This is just because of the way Python and basically every language counts the length of a list. If I say that the list has size 4, the elements inside will be 0, 1, 2, 3, because the index starts with 0. So I have to ignore the case of a value that is on the index 4, because it doesn't exist. Okay, it's running. It's giving error because, of course, the part 2 is not defined yet. Of course, I don't even see the problem for part 2. We can see that at step 9, for example, the flashes in total are 24. Let's see what was required here. Okay, after step 10 there have been a total of 24, so there is an error of offset. So the calculation is correct, which is nice. I didn't expect it to work so smoothly. But the step is 9. Why? Because, of course, the Python starts counting from 0, but human starts counting from 1. So we just change the range. Here we put 11 just to be sure. And now I see that step 10 has a total of 204 flashes, which is what the problem states. Let's see what happens. Also later it says that when we reach 100 steps, we have 1656 flashes. So I just change a bit part 1 to be sure that it works also in this case. So we see that at step 100 we have 1656 flashes, which is nice. One small thing we can do is to display these metrics a little better. So we have in part 1, instead of doing print grid, we print what? We say that for every row in the grid, so for row in grid, we print the nothing that joins the caret in the row, but row is a row of integers, and join will give us wants a list of strings, not integers, so I have to use a generator. So say the string of the string version of the number for n in row, and for on over n will be just the value, so I just printing in a different way. And this is the matrix representation, and this is the solution of our problem. So now I can use it not on the example input, but on my own real input. So I copy paste this, I put it in my input data here, and I run it. I don't remember what was it asking. It was asking how many flashes are there after 100 steps, and I get this number 1725. This may change in your case, and that's it. Oh, I'm very happy. So thank you for watching, and see you for part 2. Bye.